Hi guys, welcome back to the channel. In this video we are going to discuss about JK flip-flop. So let's get started. So first of all, if you observe, we already discussed about SR flip-flop in the previous videos. So we already see the truth table and the block diagram. Here SR means S means set and R means reset. So we can also call it as set reset flip-flop. And we also covered the D flip-flop. D means their delay. So we can call it as delay flip-flop. Likewise, similarly, we will also see the full form of JK flip-flop also. So if you observe, this is the JK flip-flop, this is the block diagram and the truth table written over there. So you can also see the truth table is almost similar to the SR flip-flop but a little change. When you pass 1 and 1 in the place of last case, in the SR flip-flop we are getting forbidden state. But in the JK flip-flop we are getting the toggle state, that is Q and bar. Remaining all things would be same. If you pass 0 0, you are going to have hold condition. If you are passing 0 1, the condition is reset. If you are passing 1 0, the condition is hit. In the last case only it will change. For that reason only we are going to use the JK flip-flop. And also very important thing, that is here JK means the scientist name, not any other name. So here JK stands for Jack Kilby, and this is the scientist image that you can see over there. So his contributions for that science, and he also integrated on in the Texas Instruments, he invented the circuit in 1958. So the JK flip-flop was developed and versatile and robust version of SR flip-flop. So after SR flip-flop only the JK flip-flop is evolved to reduce the last condition, that is forbidden state. So here we are going to have the Q and bar in the 1 1 condition to avoid forbidden state. So in his recognition, the JK flip-flop after named off. So let us quickly understand the SR flip-flop with the using gated SR latch. The first one you are seeing using NOR latch. The second one you are seeing NAND latch. So basically the first full circuit is basically SR flip-flop using NOR gates. And the second full circuit is known as the SR flip-flop but using NAND gates. So in this video only we are going to convert these SR flip-flops to our required circuits, means our JK flip-flops. If any one of you missed the videos of latches, that SR flip-flop using NOR gate, SR flip-flop using NAND gate, so please you can check out these videos. I am giving these videos in the description box, and you can also get them in the iCards also. So now let's start building the JK flip-flop using this SR flip-flop. So if you observe, just I am starting with the NOR latch. So I hope you know about this. Please check out that video before if you don't know this. So basically the first two NOR gates as cascaded, that is known as transparent latch. When you cascade with the enable line also, that becomes our gated latch. If you apply that clock transition detection circuit also, overall it becomes SR flip-flop. So a small changes for that circuit only, it becomes our JK flip-flop. So if you see, I have done nothing new. I have just added a feedback from the output to the first AND gate and a feedback from the Q bar to the next AND gate, down AND gate. And I have changed the variables as JK. That's it. That is the same thing as our JK flip-flop. I hope you understood this one. How to check this circuit whether it is right or wrong? So for checking purpose, we have already discussed the JK flip-flop truth table. This is the expanded form of the small truth table. So the first two condition is same as SR flip-flop, that is hold condition. So if you see 0 for JK, for the first two conditions, that is 0 0, and that Qn is 0 1, changing, Qn is changing. So in the output Qn plus 1, that is next state also will be having the hold condition, means the same condition you are going to have. So the next two will be reset because J and K is 0 1. The next two condition is 1 0, means Qn plus 1. The next state would be set. Whatever may be the Qn, but the next two conditions would be set. So likewise last condition is just toggle the Qn and you are going to have Qn plus 1. So toggling means what? 0 is converted to 1, 1 is converted to 0. So if you want to check the circuit diagram is correct or not, you are going to have the JK, means you are going to put the JK values in the circuit and you are going to verify Q and Q bar in the next state and previous state and now also. So like that you can confirm the circuit is true or not. But the circuit is true. You can also verify by yourself. So in the same way, we are also going to build with the help of the NAND latch also. So this is a simple SR flip-flop with the help of the NAND latch. So the first two directly cascaded NAND gates are simply transparent latch. After attaching with the two NAND gates, it becomes gated NAND latch. So finally, if you add clock transition detection circuit, it becomes SR flip-flop. So now we are going to make small changes so that we are going to obtain the JK flip-flop with the circuit. So here also I made a small changes that you can also observe there. Here also in the same way I have connected J to the Q bar and K to the Q. So remember this thing. Don't connect directly J with the Q, K with the Q bar. So here it is opposite thing. So J you have to connect all the way to Q bar and K all the way to Q. The remaining all circuit would be same. So change the S and R to the J and K. So remaining whole circuit it becomes JK flip flop. If you have any doubts regarding this circuit, you can verify the truth table. So I have already explained the truth table. First two conditions is hold, next two conditions is reset, next two conditions set, next two condition is toggle. If you are willing to check the circuit, you can put JK values in the circuit and you are going to cross check the QN and again pass that and you are again going to cross check the QN plus 1 also. So like that you can verify the truth table with the help of the circuit diagram as well and circuit diagram with the truth table as well. So basically up to now what we have saw is building of JK flip-flop circuit diagrams. So these two are the circuit diagrams for the JK flip-flop. So instead of representing these two as big circuits, we can simply represent with a small block diagram as well. So I will represent that block diagram before, I have represented before only, but for understanding purpose I have shown up to this derivation of the circuit from SR flip-flop to JK flip-flop. So if you observe, these are just simple circuits, that is with the help of the NAND latch, NAND gated latch, and second one is with the help of NOR gated latch. So these whole two circuits are same, that is JK flip flop only. So the next thing we are going to see is JK flip flop characteristic equation. For that we are going to have the truth table. So in this case we are going to call it as characteristic table. Also it can be called as. So if you see the first column, that is Qn, the present state. So JK and the next state, that would be Qn plus 1. So basically characteristic equation means expression of, means the output expression in terms of input and the present state input and the inputs, means the Qn plus 1 in terms of JK Qn. So that can be obtained with the help of truth table only. So for the first two cases you are going to have the min terms. So it is not like general normal min terms, because you are going to see according to the inputs. So if you observe the second one, that is 100, that is 4 according to the decimal form. So that is why I am representing M4, that is min term. And the min terms we have 2, 3, 4, 6 in the positions. And the outputs are same, Qn plus 1. First two conditions hold, next two conditions reset, next two conditions set, and the last two conditions would be, that is toggle condition. Now we are going to fill these all min terms in the K map and we are going to have the output expression Qn plus 1. So here is our K map. If you observe, we have min terms 2, 3, 4, 6. I have filled 2, 3, 4, 6 in the K map. As we have only 3 variables, I took Qn in the row wise, JK in the column wise. You can also observe we can make group of 2 elements, that is 2 groups. 3 and 2 can be made as green group, that is JQn bar. And 4 and 6 can be made as corner grouping, that is blue color group, that is K bar Qn. So output expression is that. So that output expression is also known as characteristic equation. Now you might get a doubt that why we need this characteristic equation. So suppose assume that you don't know the truth table. So instead of having the truth table, just with the help of this characteristic equation, you can have the present state and the next state outputs as well. So if you observe, I am putting JK values from 0, 0 to 1, 1. So simply I am putting all the values in the Qn plus 1. You are going to obtain simply the next state output. So first you can observe that the Qn plus 1, that when I put J is equals to 0 and K is equals to 0, I am getting Qn plus 1 is equals to Qn. So J is equal to 0, K is equal to 1. In that situation, I am going to have Qn plus 1 is equals to 0. So likewise, if you put J is equal to 1 and K is equal to 1, you are going to have Qn plus 1 as Qn bar. So likewise, all outputs are, if you compare with the truth table outputs also, the same outputs we are going to have. So that is the reason we are going to have this characteristic equation for the simplicity purpose. So the next thing is JK flip-flop excitation table. So we already saw up to now the characteristic table and characteristic equation. So now we are going to build the excitation table. So what is meant by excitation table first? So it is nothing but expressing the inputs in terms of outputs, or we can simply say, so for what, so outputs we have, for what outputs we are going to have the corresponding inputs. So we have the output Qn. For going to the next state Qn plus 1, what we need to have the inputs. So that is the thing that we are going to find with the help of the characteristic table. With the help of characteristic table only we are going to build this excitation table. And these excitation tables are very much used in the flip-flop conversions. So in the upcoming videos we are going to see the flip-flop conversions from SR to JK, JK to SR, SR to D, D to SR, like these kind of conversions. That kind of conversions needed this excitation table. So these excitation tables are very important. So let's see this. So I already said for the building of excitation table we need the characteristic table. So I could took the characteristic table. So if you observe the first row, we have 0 is changing from 0, present state 0 qn, changing to next state 0, that is qn plus 1. So for that what we need to have jk. So if you observe qn plus 1, we have two 0 0 conditions, that is in the first and the third, means the second position. So according to corresponding to that, we have what is the jk inputs, that is for first corresponding jk is 0 0, the next third corresponding jk is 0 1. So j is same, not changing, k is changing. So in the output, means in the table we can represent as j is 0 and k is don't care condition, because k is changing. In the same fashion, if we observe for 0 is changing to next state as 1. So in the corresponding, in the characteristic table also you are going to have that, and you are going to compare the inputs and you are going to fill this excitation table. So according to 0 1 we have two positions over that. So if you compare jk, so first jk is 1 0, next jk is 1 1. If you observe j is not changing, k is changing. So in this case also we are going to have j as 1, k as don't care. So the next state is the present state 1 changing to the next state 0. For that we need to find jk. So if you observe in this truth table, again we have two cases, that is 1 0, the first highlighted one, and the second highlighted one. So corresponding jk would be 0 1 and 1 1. So here if you observe, j is changing from 0 to 1 and k is not changing, that is 1 only. So in the truth table we are going to fill with don't care 1, because k is not changing there. So the final case is corresponding to present state is 1, next state is also 1. So for that outputs we are going to check the inputs. So if you observe, j is, means jk was 0 0 and the next case jk is 1 1 0. So j is changing, k is not changing as 0. So fill that as don't care 0, because j is changing. So j is don't care, 0 is not changing as 0. So k is 0. So finally this is the excitation of jk flip-flop. So practice once or twice this excitation table. So this table is very much important in the flip-flop conversions. So conversions might be asked in your university exams or some of the gate exams, that high level exams. So next we are going to see is jk flip-flop timing diagram analysis of output. So if you consider, first I took positive edge triggered. So we have as 3 inputs total. The first 2 inputs are general inputs, that is jk. So if you took, if you see, I have took some random inputs, so random clock pulses. So I have took some clock pulse also, because we have some clock over there. I forgot to mention, as we have 3 inputs and 2 outputs, that is q bar, we are going to obtain the output expression q. For that we need to have the truth table of the jk flip-flop. So this is the simple jk flip-flop truth table. First condition is hold, next is reset, next is set, and finally is toggle condition. So if you see, I have arranged all the inputs and the clock pulse according to the correct manner. And if you also see, observe clearly, I have took the positive edge triggering. So clock is, we have to consider when rising edge. So the first itself it is rising edge, then j and k we need to consider. So j is 0 and k is 1. For that conditions we are going to check the truth table and we are going to follow our output. So if you observe, when j is 0 and k is 1, the output is 0. So until the next rising edge we are going to have the output q as the falling edge, means the low level only. So if you see here, in the next rising edge of clock, you can consider that j and k, that j is 1, k is 0. Again you are going to compare in the truth table, that again it is increasing, means it is high in this case, when the j and k is, j is 1, k is 0. So in the output expression also you are going to raise our output to high level until you see the next rising clock edge. So finally if you see the last rising edge go up to there, and you are again going to compare j and k, j is 0, k is 1. So again you are going to come back by comparing the truth table as well. So as we have two outputs, that is q and q bar, so simply invert the q, that as high as low, low as high, again you are going to get as q bar. That is the simple conversion. So in the jk flip-flop we have 2 outputs, that is q and q bar, and 3 inputs jk and clock. So next thing is race around condition in jk flip-flop. So what is meant by race around condition? So I hope you might heard about this conditions in your classes or any might hear. So let's see what is meant by race around condition. So this is the jk flip-flop that we already saw. So if you consider, I have not drawn their clock transition, means the circuit over there, because this is, we are going to pass the level triggered clock. So in the timing diagram analysis we have saw the edge triggering. Suppose if you pass the level triggering, in that in that circuit, then we need to means we will obtain a condition called race around condition when you pass both the inputs as 1 1. So occurs when output of flip flop changes multiple times with a single clock cycle due to the propagation delay being shorter than clock pulse duration. So we will simply understand with this diagram, means timing diagram analysis as well. So you can also observe here when we are passing J, K, so when the clock also is passing, so the output is changing multiple times in a single high level in the clock if you are using level triggered. Level triggered, and when you are passing both inputs JK as 1 1. So this is very important and peculiar situation that we need to understand. So that is the reason we are not going to use the JK flip flop if level triggered is used. So majority of the cases we are going to use only the edge triggering for the JK flip flop. So this is the thing I am saying about. So solution for race around condition. How we can avoid that race around condition. How we can avoid the changing of multiple times output in a single level. So instead of using the level trigger, just use the edge triggering clock. Simple that is. So the second solution is use master slave flip flop to avoid the race around condition. So if you want to use the just JK flip flop with the means I want to use just JK flip flop or I have only JK flip flop. So how to avoid the race around condition? That is the scenario you can use the edge triggering. So the next case is you have the master slave, but you need to pass the level trigger, but you need to obtain the correct output. Then you can use the master slave flip flop. By using the level triggered only, you can get the correct outputs when you are passing JK as 1 1 only. So master slave is nothing but just the extension of JK flip flop only. I hope you understood this JK flip flop very much well. Thanks for watching up to now.